Section 5.4, page 6. All right, on page 5, we had just derived a piece of information about area of an added-on section, and we ended up with that bit right there, that f of x was equal to f prime of x. All right, now, would you agree with me that this f prime of x is the derivative of f of x? Yes. And then, if we replace this big f of x with what it was defined as, we have this, d dx of the integral from a to x of f of t dt. And pulling this all together, then we have this, f of x is equal to d dx of the integral from a to x of f of t dt. All right, so here's what this says. If you want to evaluate something like this, if we do an integral on some f of t, get an answer, then do the derivative of that answer, well, we get right back to that f function. See this f right here and this f right here? So the derivative of an integral is the function itself. And again, I know that's fuzzy right now. Let's just start working through some problems. If we look at this first one, y is the integral from 1 to x of 3t squared plus t dt. And I want you to find the derivative of that y. Well, first, let's actually figure out what y is. So, y is this integral. Let's go ahead and do this integral. And let's see that the antiderivative of this 3t squared is x cubed. Oops, not x, because we're in t's. T cubed plus, and the antiderivative of this t is 1/2 t squared, but we're evaluating that from 1 to x, which means we're going to plug in that x first, x cubed plus 1/2 x squared minus, now plug in the 1 cubed plus 1/2 times 1 squared, and we will have x cubed plus 1/2 x squared minus 1 plus 1/2, 3/2. Fabulous. That's just y. But I want you to find dy dx. So finding dy dx now, do a derivative of that function, and we are at 3x squared plus x. All right, now look please. Original problem. Down to the answer. What do you see? Hopefully you see that all we did was take out this t and replace it with an x. So that's 3x squared plus an x when we did the derivative of this integral. When you do a derivative of an integral, you can just take this x and replace it in place of the t's. Be very, very careful. Look at this next one. Watch your notation very, very carefully here. If y is the integral from x to 1 of 1 over t dt, where x is greater than 0, I'm just avoiding that whole asymptote thing on this function 1 over t. Let's find the derivative. First thing that we see with this integral is that the bounds are backwards. We're supposed to have a constant on the bottom and a variable up top. So you remember that if we flip the bounds around, it changes the sign of the integral. All right, now let's do a derivative. Don't just slap down negative 1 over x. Watch your notation. dy dx is, we have to do the derivative d dx of negative, the integral from 1 to x of 1 over t dt. The derivative of a negative function, that negative just comes down. Now you're doing the derivative of an integral. The derivative of an integral, you can take that x and replace out this t. So we have negative 1 over x. That's it. All right. Look at this next one, number 10. Now again, notice we want the derivative of this integral. Just written it a little bit different, but derivative of an integral. And we see we have a constant on the bottom, that's good, but we have this 2x up here. So we have a little bit of an issue there. It's the same basic process, there's just one little extra step. When you're doing this derivative of an integral, you can take this 2x and put it down here in place of that t. So that's going to be cosine of 2x. However, because that 2x was here, we're going to need to multiply times the derivative of that 2x. So times a 2. We have 2 cosine 2x. And again, this 2, we have a little bit of a chain rule going on here. This 2x is in place of an x, so we have to multiply times its derivative. It's a chain rule going on. All right, looking at number 11 here. We have y is the integral from sine x to cosine x of some t squared dt, and I want you to find dy dx. Well, that means that dy dx is d dx, or the derivative of this mess, but we have a problem here because this lower bound is supposed to be a constant, and right now it's not a constant, so we have a problem. Let's come over to this side over here and sketch a graph of y equals t squared. And thinking about what this is describing the area underneath that curve from sine x to cosine x. All right. Remember, our issue was that we didn't have a constant on the bottom. So could we think about this same area right here as the area from, oh, I don't know, say 0 to cosine x minus the area from 0 to sine x. By doing that, that introduces that lower bound as a constant, dy dx. So let's do the derivative of the integral from 0 to cosine x underneath t squared dt minus the integral from 0 to sine x t squared dt. Again, area from 0 to cosine minus area from 0 to sine. And you can separate that over derivatives over an addition and subtraction sign. Now we handle each piece separately. And we see this pattern. We're doing the derivative of an integral. So we can take that cosine x piece and replace out this t, which will give us cosine x quantity squared, but then times the derivative of the cosine. And the derivative of the cosine is negative sine. There's that first one. Looking at this second one here. Replace out the t, this time with sine. So we'll have sine x quantity squared times the derivative of the sine, which is cosine. In cleaning this up then, this will give us cosine squared x times sine x minus sine squared x times cosine x. You could factor out a, lost a negative sign here, right there. But found it before we got too far. You could factor out a negative sine x cosine x, but it's not going to help you. I would stop right here. Okay, hopefully this page helped clean up a little bit about that first fundamental theorem. More to come. Join me on page 7.